Hello and welcome everybody to another of our Kickstarter Science Colloquium. As usual, we'll start with the usual range of reminders. We are recording all of these colloquia so that the recordings can be posted on YouTube for the benefit of the wider Rubin community at a later date. So if you prefer not to be recorded, then feel free to keep your camera off. And if you are not the one speaking, then please kindly mute your microphone so that we don't get in the background noise. That said, you are welcome to post questions to our speakers at any time using the chat feature, and we'll make sure that there's plenty of time to answer those questions later on in the colloquium. So today I'd like to give a very warm welcome to two speakers that are representing the group from University of Washington, Sarah Greenstreet and Joachim Moeyens. They've been making software more accessible to the wider community is a really important element of increasing participation in science generally. And that's particularly true when the package involved is particularly specialist software. Sarah and Joachim are going to tell us about their progress with a package designed to fit the orbits of solar system objects. So with that, welcome Sarah and Joachim, and take it away.
Thank you, Rachel. Okay, it looks like we are all set. Hopefully everybody can see our slides here. Okay, well, hi everyone. My name is Sarah Greenstreet. As Rachel mentioned, my co-presenter today is Joachim Moeyens, who is a University of Washington graduate student who's actually just finishing up his time as a graduate student, having just defended his thesis a couple weeks ago. Also, Aidan, Berres, and Aditi Chauhan are two former University of Washington undergraduate students who actually performed the vast majority of the work that we're going to be talking about today. They've both since moved on to other positions, so Joachim and I are presenting this work in part on their behalf. We were fortunate enough to receive funding through the Kickstarter program to do two projects, which are both rather closely related to each other. So we're going to be talking about both of them today, where our main overarching goal, as Rachel mentioned, is that we really wanted to make it easier for people in the community to be able to install, use, validate, and compare results among the various orbit fitting software packages that are available to the solar system science community. Which is going to be really important in the era of LSST and doing science with that data set. So I think we're all very familiar with the Legacy Survey of Space and Time, or LSST, which will be a multi-band photometric survey conducted by the Rubin Observatory over a 10-year period, and is set to start just 2 short years from now at this point. LSST is expected to observe something like 20 billion galaxies, 17 billion stars, and 6 million small bodies across the solar system, producing something on the order of 20 terabytes of data every single night. So an incredible data set. There are 4 main science drivers for LSST. The one that is important in the context of this talk is the goal to be able to improve the inventory of small bodies across the solar system. So to try to quantify this for you, here are some of the numbers of the currently known objects in various dynamical small body populations across the solar system. We currently know of thousands to tens of thousands of many of these objects. There are more than 1 million known main belt asteroids, but all of these objects, these numbers are going to be dwarfed in the era of LSST, which is expected to increase the number of known objects in these populations by a factor of several to an order of magnitude or more. Next slide, please. So in LSST working to improve this small body inventory, this is going to consist of millions of discoveries of small bodies over the 10-year time period by taking nearly 2 billion observations of these roughly 6 million expected small bodies. Now these, the orbit catalogs, color and physical property information for these small bodies is going to enable a huge amount of solar system science. Largely in the big picture, this is going to help us be able to better understand both the formation and evolution of the solar system. On a smaller scale, in looking at more individual objects within these populations. Next slide, please, Joachim. This huge data set with these millions of small body discoveries, these objects are very likely going to include a huge number of objects in these detections that are going to be really interesting for doing further study beyond just being able to add them as a number to this inventory list of more objects discovered in the solar system. This can include wanting to refine their orbits in order to, for example, be able to better constrain the impact probability for potential Earth impactors, or do the same for objects that are discovered on incoming impact trajectories, for which a few such objects have actually been discovered so far, or being able to better understand the orbital evolution of these objects, either over long time periods or even much shorter time periods, which can especially be important for things that we can only observe for a very short amount of time. Even with LSST, this can be especially important for things like interstellar objects, where they're really only visible to us for a short amount of time while they're actually visiting our solar system and close enough to the Earth where we can see them. It's also very likely that this incredible Rubin data set is going to have a huge number of objects that are going to be present in the data, but that won't actually be extracted by the detection pipelines for a number of various possible reasons, but will still be sitting there hidden, waiting for somebody to write the code to be able to extract those detections out of the images and link those observations together and determine orbits for those objects. So all of this science together is going to be really important for LSST. It's going to help us be able to improve the inventory of these solar system objects. Next slide, please, Joachim. So in order to do all of this science and improve this inventory, we really need to be able to not only take a huge number of observations of these objects, which LSST is going to provide, allowing us to discover and track these small bodies, but we also need the ability to be able to link observations of objects that move across the sky as belonging to individual objects, and then take those sets of observations that belong to a given object and determine their orbits around the sun in order for us to be able to know where they're going to be in the sky at any time in the future, so that we can find them and those discoveries aren't subsequently lost down the road. So this last piece that is most relevant for this talk today requires the use of orbit fitting or orbit integration software. Next slide. So there are a number of these orbit fitting software packages that are currently available and widely used across the solar system science community. The three most commonly used ones are on the right-hand side here. These all work generally really well. Most of them work as we would expect, straight out of the box, as you might say, using their default configuration settings, and everything working the way we expect. However, there are times when we discover objects that are really difficult to determine orbits for, and that can require users of these orbit fitting codes to potentially need to modify the code in order to actually be able to get trustworthy results back out. In addition, each of these codes on the right here use different techniques or methods for being able to compute orbits for an object given a set of observations. And that can lead to varied levels of performance between these different codes when fitting orbits to objects that belong to different dynamical classes across the solar system. So for example, one of these codes might be better at being able to fit orbits to near-Earth objects than the others may be. In addition, on a much more fundamental level, many of these codes are not very simple to be able to actually get started with using. Most of them don't provide very good documentation on how to install them or get started with them, or don't provide very simplified processes by which to be able to install and get them set up and actually start using them. So next slide, please. So all together, these challenges can lead to a number of questions for users of these codes, and not always just new users of these codes, but anyone in the community. So this can lead to questions such as, how do I know when I'm using one of these codes that I may need to actually make some of these adjustments to the code to get it to produce trustworthy fitted orbits coming back out for me? That then includes or is similar to asking the question of, how do I know if I can really be confident in the results that I'm getting back from these codes? In addition, not knowing how to get access to that information is another part of that, as well as not knowing whether a person would need a rather high level of experience working with these codes or knowledge in how these codes actually function in order to make some of the potential needed adjustments to those codes to get them to work reliably. In addition, since these codes can perform at various levels for different objects in question, it can be difficult for users to be able to know which of these codes actually perform best in fitting an orbit for an object that I might be interested in studying. And if that code that might perform better than the one that I am currently using is not already something I have access to, how do I get access to that code? How can I easily install it and start using that one that's actually better than the one that I have access to currently? So altogether, all of these questions and these challenges can really leave users potentially feeling like they're lacking quite a bit that could have an effect on their ability to make discoveries or do science, especially with the Rubin data set, which is, of course, something that we want to try to avoid. So next slide. So all of these questions and these challenges together can lead to a situation where there's really only a small number of users within the science community that can very confidently and reliably use these codes, who have a high level of experience working with these codes and knowledge in how their orbit determination calculations actually work. So our goal with these projects that we're going to talk about today was to try to improve this situation by increasing the confidence in being able to use these codes to a much broader, more diverse group within the science community, namely opening it up to anybody in the science community to have the ability and have access to the information that allows them to be able to confidently use these codes for their science and their discoveries. So the first of these projects that we're going to talk about is our construction of a verification and validation testing framework for the 3 orbit fitting software packages that are most commonly used by the community today. This work was largely done by former UW student Aidan Berres, who's now a graduate student at UIUC. And the other piece is to try to simplify the installation and setup processes for these codes so that it's just easier to use them in the first place, where this work was largely done by former UW student Aditi Chauhan. So now I want to pass things off to Joachim, who's going to talk about this work in more detail.
Yeah, thank you for the introduction and the lovely overview of the 2 different projects here. So before we delve into detail for the first project, I do want to quickly kind of reiterate some of the uses for orbital integrators. And from our standpoint, it really comes down to understanding how well orbital integrators perform in 3 different tasks. And that first task is going to be orbit propagation. Orbit integrators need to be able to accurately propagate orbits forward and backward in time over the course of decades through the solar system, right? We're not talking here about doing evolutionary studies where we're talking propagations on the order of millennia and millions of years. For our use case for LSST, we really care about those propagators that are accurate over the course of decades. Another thing that's really important that these orbit integrators have to be able to do is give you accurate predictions as to the on-sky location of moving objects, right? So this not only means you need to be good at propagating, but you also have to have an innate understanding of where your observatory is in space as a function of time. And then lastly, for actual discovery, we need to be able to determine orbits from observations. sometimes called observation inversion. And so these integrators and these orbit fitting packages, given a set of observations that you believe belong to a single object, have to be able to calculate the orbit that could represent those observations. And this also has to be done in the presence of outliers and false positives. And so that makes this a even more complicated problem. Now, you look at these three different functions and these three different kind of overarching ideas that these orbit integrators have to address. They all have some underlying implementation details that really end up mattering. And those are the kinds of things that we also want to be able to test. So the first kind of consideration that you can think of is, how is your force model implemented, right? Do you want to take into account the largest, 300 asteroids when you're calculating the perturbations that you would impose upon a, say, test orbit? You also have to take into account the perturbations by the planets. Other considerations include things like relativistic effects, time dilation. This is extremely important for things that are like satellites that are in Earth orbit, or as you approach the sun, where the mass of the sun actually causes measurable relativistic effects on your orbit. Other things is, the planets are not perfect spheres. They are oblate spheroids. That means that their mass distribution actually really matters and has an effect on a orbit as it's being propagated through a close encounter with that planet. And so you have to be able to model that as well. There's also some of these software packages, they take pride in adding things like non-gravitational effects. So we're talking solar radiation pressure, and being able to model that effectively as well. Of course, so these are just force model implementations. You also need to be able to actually know where the planets are. And what this typically means in these kind of use cases is you're interacting with the JPL ephemeris files. And so this means that you're reading those files, you're querying those files for the predicted position of the planets, and so you're then using those as inputs to your force model implementation. And of course, so these JPL ephemeris files, they give you the location of planets, but they don't give you the location of the observer. So now you have to write some code on top of that to actually calculate a topocentric offset, so you can accurately calculate where the observatory is in Cartesian solar system space. And so we're talking accuracies here on the order of centimeters. That's what you have to be able to achieve to be able to get this done accurately. There's also weird things to consider, like aberrations, right? In astronomy, we're always observing the past. That is true for the solar system as well. It takes time for light to travel. For asteroids, it's typically minutes to hours, and at the far reach of the solar system, it is days. But you have to be able to accurately calculate the light time lag, and this has all kinds of nuances. You have to be able to transform your frame of reference to an inertial system. In that inertial system, you're going to need a two-body iteration schema to be able to calculate how much light time lag you have to add to your orbits. So it gets complicated very, very quickly. And then lastly, there's also these weird oddities, and Sarah already mentioned some of this, but basically not all orbit determination techniques work equally well for all populations of solar system objects. It is also true that not all orbit determination techniques work for your different observing cadences and your observing constraints. And so you have to take all these different things into account when you're testing and building these kinds of packages. And the impression I want to leave you with here is that all of this leaves room for many bugs to be implemented, accidentally or otherwise. And so that means you need a lot of know-how and a lot of expertise to be able to go in, read these codes, fix these codes, and understand that they're actually working as they were intended to be working. And so that's kind of what we wanted to set out to change. We wanted to build some kind of framework where we could test that these codes are working as they were intended to. To give you an indication of kind of the usual suspects in the field, so these are the three most common Orb integrator packages. We have at the top end FindOrb, which has really been adopted by the NEO community. This was written by Bill Gray in C and C++. This is actually a phenomenal package. This was able to actually accurately calculate the impact location of an asteroid, which became a meteorite in South Sudan, I think in 2008. Another example is OpenOrb. OpenOrb here is considered a lot easier to use. It's a lot easier to install, and it's typically used for things like population studies. This was written in Fortran 90 and has already been partially exposed in Python. And then finally, kind of to the last one to build the trifecta is OrbFit. OrbFit was made by Andrea Milani and company at the University of Pisa. So what's amazing about this code is this is actually now the code that's being used by the European Space Agency and also the Minor Planet Center. So it's important for us to also understand how well that works. Unfortunately for us common folk, we don't have access to that version that they use. And so the one that we have access to is a one that's available on Bitbucket and is at this point many years out of date. Nevertheless, people do use it, and so we also wanted to test that today. All of these packages have different implementations for your force model. They're very different underneath, but the one thing that they have in common is that they have no unit tests, okay? I'm going to say this one more time. They have no unit tests, and that should scare you, and that scares me. This is the stuff of my nightmares, because I don't know which of these packages to use for what population of solar system objects. I don't know if these packages are doing what I think they're doing, because there's no way for me to know, because there's no unit tests. And that's scary. And that also means that if you're going in to change these packages, you have nothing to test against, unless you're coming in with your own integration tests. And so this is also something that we wanted to change. We wanted to come up with a schema where we're not necessarily contributing unit tests, but we're finding a way to test these codes without going into the nuances of the actual languages that they were written in. Okay, so what did we do? We built what we like to call orbit integrator testing, or Orbit for short. This was done by Aidan Berres at the University of Washington. It's an open source Python package that wraps the three most commonly used orbit integrators and fitters, the ones that I mentioned from the slide before. And what it provides is a testing framework that tests for the internal consistency of the underlying orbit integrators. And I'm going to go into a little bit more detail as to what that means in a bit. Now, I want to share our design philosophy or design considerations while we were building this. So the first thing we wanted to make sure that we did was we wanted to leave these propagators and integrators as out of the box as possible, because that represents the most common use case. And Sarah's already said this, so I'm going to reiterate it here. Most people, they will just download these codes and use them as they are without any configuring. And we wanted to make sure that we replicated that behavior here. If we did make any changes, the only changes we ever made were to the configurations of these codes so that we can map them to use a common set of inputs and outputs, effectively create a generalized interface to all three packages so that we could directly compare their results against one another and against our testing framework. And then finally, and this is very important for development, we wanted to make sure that any testing that we do could be reproduced with minimal effort. And I have to give a huge shout out to Aidan here. He did phenomenal work in getting this working, because basically the way that we do this is as we're running our end-to-end test, all of the intermediate products made or produced by these integrators are saved into a directory. And then he goes one step further and he creates a series of bash scripts that reproduce the exact commands you would need to reproduce the entire experiment. Those are all tarballed into a single folder, and you can then send that folder to the author in question and actually have a discussion about, how this the results of the test and how it should have performed, and actually give them a test case that they can use. And this is especially important when you don't have unit tests that you can fall back on. Okay. All right. So what is this kind of end-to-end test? And so what we like to call it the complete the loop test. And so our goal was we came up with this test to try to test the three key functions that these orbit integrators provide. And so for any representative set of input orbits, and these can be user-defined, or there's also ones that ship with the repository, what we end up doing is we create a set of simulated observations for each object. And we do this for a variety of different observatory codes and a variety of different time deltas or observing cadences. And at the practical level, what you can imagine that we're doing is we're calling some magical function called integrator.generate ephemeris. We give it the orbits, it generates the ephemerides, we have these simulated observations. After that, we can then optionally decide, hey, let's add some astrometric errors or not to those observations and see what the impact is on the end result. That we do this because in reality, all of our observations have errors, so we might as well also see how these codes perform in the presence of those errors. Finally, what we do is we fit those observations and we determine what the best fit orbit is using the orbit determination component of the integrator. Now, because of the way that orbit determination works, the actual best fit orbit that is produced is typically defined at a different epoch than the input truth orbit. And so we have to do one additional step where we actually propagate the truth orbit to the time at which the best fit orbit is defined. And at that point in time, you can actually calculate the vector difference between the two and calculate the offset, and we can report that back to you. And so we can also visualize this as rather than just having words on a slide. So you have your input orbit mapped onto the sky. You use that input orbit to generate a series of observations here depicted in red. And a detail to note here is we don't care about the force model implementation. That's why we call this internal consistency. We're letting the actual propagator decide what force model they want to be using. But we, fundamentally, it should be able to reproduce the input state vector regardless of what force model it's using. That's just the way that this should work. So once we have our simulated observations, we will then fit those. And typically in the presence of errors, you'll see an on-sky residual. So here we see that the blue points don't quite overlap with the red points, but that's just the nature of orbit fitting in the presence of errors. These observations then give you access to what you believe to be the best fit orbit. If we zoom in real quick, we can see that the truth orbit is defined at a different epoch than the best fit orbit. And so then we simply just propagate the truth orbit to overlap in time with the best fit orbit. And at that point in time, we can actually calculate the vector difference and report that result back to you. And so this is what we call the complete the loop test. And one thing I want to point out here is I've highlighted those magical functions, right? Integrator.generate ephemeris, integrator.orbit determination, integrator.propagate orbits. And so one of the things that we did, and this is really, I think, one of the most substantial contributions that Aidan contributed here, is we created a generalized backend system that maps or effectively creates a common interface to all of these different propagators, because we believe fundamentally that in order to use these propagators or swap between using propagators, it should be no more difficult than changing just a single line of code, right? So if I want to go from using findOrb to using PyOrb, I don't want to do anything more complicated than that. And that is the system that underpins this entire architecture, this generalized backend class. So if you don't want to use necessarily a testing framework, but you want to access the backend class, that Orbit can do that for you as well. Okay. What does actually a test look like in practice? Here is the minimal amount of code you need to do to actually reproduce a full end-to-end test in the Orbit framework. So you're importing your typical packages, NumPy, that's just a standard package. And then from Orbit, you're importing the backend classes. So that's the PyOrb, findOrb, OrbFit. You're importing an orbits class. In this example, we're actually loading orbits from a CSV that ships with the repository. So there's no reason you can't just instantiate these orbits from Horizons itself. And there's actually functionality built in with Orbit that allows you to load orbits from the Horizon service. Once you have your orbits, and we believe that these orbits roughly are representative of the population of the solar system, you then have to define your observing assumption. So here what we're seeing is we're defining, we want to have observations once a day for 30 days. We want to iterate over a bunch of over 3 different astrometric errors in milliarc seconds. So we want to have 0 error, 10 milliarc seconds of error, 100 milliarc seconds of error. In this case, we're only iterating over a single observatory code. That's just the geocenter, but you can imagine adding more. And then finally, we want to iterate over the following integrators, which in this case is just going to be findOrb. But there's no reason you couldn't add PyOrb to that list, OrbFit to that list, and see how all of these perform on the same set of objects, the same set of observing conditions. Once you have all of these things defined, you run a single command and it produces something like this. So here's an example result from that run test function. It's a pandas data frame, and I'm just going to walk through kind of all the things that we can see here. So I already alluded to this, but you can test different objects. So in this case, we're seeing 3 different objects, each represented 3 times. That's because we varied the astrometric error. And so we can see what the effect will be in just a second. You can see what integrator you're using. So imagine if I added more integrators, you'd also see OpenOrb and OrbFit here listed as well. You can iterate over the observatories. In this case, we're just doing the geocenter for simplicity. You can have different assumptions on the observing cadence and the number of observations total. And finally, and this is what we varied actually for this experiment, we can see the impact of different astrometric errors on the experiment. And in terms of what the actual results are, so these are actually truncated. There's more columns that are added in this data frame. Right here, I'm only reporting the offset in position, which is the magnitude of the vector, and the offset in velocity. And so we can clearly see that for this particular asteroid Evisdich, for the integrator findOrb at 0 milliarc seconds of error added, so these are perfect observations, we can see that it's able to reproduce the state vector to within fractions of a millimeter, okay? This is actually numerical precision for findOrb, because findOrb stores its distances in AU, and so if you represent a millimeter in terms of AU, you're roughly at the limits of numerical precision for this particular test case. What is striking here, and this is kind of a testament to the power of a data product like this, is you can clearly see that it quickly devolves, right? As you increase at your astrometric errors, your offset between your best fit states and the truth state starts to increase rapidly. And at 100 milliarc seconds, we're talking a 15,000 kilometer offset, right? For the asteroid Lydia, we're talking about nearly a 40,000 kilometer offset. And so this is just kind of, this is a dummy example that we're showing here, but this shows you the power of a testing framework like this. And a huge credit to Aidan who figured this all out. And so, of course, now what that means for us as scientists, we can come in and say, hey, look, this integrator is working really well for these NEOs. We should be using FindOrb for NEOs, or we should be using PyOrb for NEOs. And so that really gives you access to a lot of information, and it allows you to make informed decisions as to what integrator is best served for the population that you're interested in. Okay. Okay, so that's Orb It. But before you can even ever consider doing what we were just talking about, like these really cool, fun analyses, you actually have to be able to install these codes. And so this leads us into talking about project number 2. This is the kind of, this is what you have to do to get FindOrb installed. And this is already assuming that you have all the system level dependencies installed, right? This is not easy. This is cumbersome work. And there's no guarantee that you're going to run these commands and they're going to execute successfully. And we believe fundamentally that this should not be more complicated than just running this, right? This is what you should be able to do to get to your science. Run a single command that installs this propagator and has it ready for work, right? And so that's what this second project tried to address. We wanted to go from things like this and make them things like that. Very simple, effective, easy access to your underlying propagators. So before we started, we kind of did a census of the most common kind of sources and small body packages that people use, and that's depicted in this table here. The ones that are highlighted are the ones that we end up kind of focusing on. And so we started off by looking at SPPy, which is a Python package to do kind of small body astronomy. And then there's also FindOrb and OpenOrb, which we just kind of mentioned as 2 different integrators. And then at the bottom, we see Rubin, Sims, and MAF. At the onset of this project, Rubin, Sims, and MAF were 2 separate packages not available on CondaForge. So they were not available to be installed via a command like this. But while we were working on SPPy, FindOrb, and OpenOrb, the developers of those packages actually went through, restructured them into a single package, and made it installable on CondaForge. And so that's already a success for the community, and that somebody else already went through and made that code more installable. And for us, it was a stark reminder that people are interested in doing this, right? There are people out there doing this. And so it made us, it motivated us to keep at this. But so basically for the duration of the project 2, we focused on getting SPPy, FindOrb, and OpenOrb installable with something like that. Okay, so let's talk about SPPy real quick. So SPPy was the first project we decided to tackle, and this was done completely intentionally in that SPPy is a pure Python package. So the architecture of the system on which you're building is irrelevant. As long as you have a Python installation, you should be able to install this code. And so this was really a good candidate for us to really learn how to do this kind of open source software packaging with Conda. And Aditi, who didn't have any experience in doing this, really viewed this as the package to use to learn how to do this procedure. Okay. So what were our deliverables in the end? So what we ended up doing is we wrote a Conda recipe, which effectively contains the build instructions for how to build SPPy as a CondaForge package. So this means you're creating a description of where to get the dependencies you need for that package, how to build those dependencies, and how to actually install this SPPy package into your environment. Once you have this CondaForge recipe, what you typically then do is you submit a pull request to the CondaForge organization, and then they'll review that pull request, and then if they like it, they'll incorporate those changes, and then at that point in time, it becomes a one-liner to install your code. So we got to the pull request, we go to submission, and unfortunately, it was denied because it was marked as a duplicate. And it just turned out that a few days prior to us completing this particular project, a member of the community had already submitted a completed version of the pull request, and that had been incorporated. And so even though this was kind of a loss for us, it was a little bit of a heartbreak for us, in the end result's the same, right? We still have access to this code. As members of the community, we have access to this code, and now we can tick this box. Not all is lost though. This was a great learning experience, and indeed learned a lot about the procedure that we would need to do to be able to get these things packaged. And so if you're to ask me about, what the status of this project is, I do complete asterisks because we did achieve it. We just weren't the ones that end up getting credit for it because somebody else had taken it through to completion just a few days prior to our submission. Okay, that was SPPy. First package success, we're good. Let's talk about OpenOrb and FindOrb. And now things kind of just get a little bit more heady and more unfortunate. So a couple of details to understand. These are codes that are written in statically typed languages. So Fortran 90 and C and C++ respectively for OpenOrb and FindOrb. That introduces a whole new set of variables to your build equation. That means now the compiler matters, now the system on which you're building matters, and the system level dependencies also matter. And that makes it a whole lot more complicated to deliver this as a Conda installable package, right? For an added complication, to get this stuff pushed to Conda Forge maintains their own list of dependencies that they consider stable. These are not the same dependencies that you and I would download on any given day, right? When you're doing Conda install package name, you're doing Conda install package name assuming you're getting the latest version of that package. Conda Forge pins packages of certain versions that they consider stable. And so that means that there's another variable that you're adding. You're not only adding the compilers and the OS and system level dependencies, you're now adding the actual version pinning that Conda Forge provides, right? So that adds another level of complication. And as I stressed earlier, none of this is unit tested. So that means that any change you make to the source code, you cannot test in terms of the output product, right? So you can test whether it compiles or not, but you actually can't fundamentally test if you've broken the code or not. And so that relies on Aditi and I actually running test things through to make sure that the underlying code didn't break. And so that made it even more tedious to deal with. Okay, so that's kind of setting up the scene here for what's about to follow. So let's talk about FindOrb. FindOrb, we didn't actually have to start from scratch, thankfully. My PhD dissertation advisor, Professor Mara Juric, already did this a few years ago, but the starting place he gave us was already out of date by hundreds of commits. The author of FindOrb is like almost a commit a day kind of person. Like he's changing that code daily, which means that we need to put a lot of effort in this to keep up with his updates. And so what we ended up doing was we took that as a starting point, and now we actually have to go in and make modifications to the source code. So to the C++ source code to be able to get it to compile against the Conda Forge compilers. The way that this is delivered is there's a philosophy here that's important to follow, where if you're making any changes to source code, you can imagine actually submitting those as a pull request to the home repository. So you can imagine that we might consider submitting the changes we made to the source code to make it compilable on Conda Forge to FindOrb. But that's actually the incorrect philosophy here, because these changes are specific just for the Conda Forge build. And so the way that you deliver these changes is you store them in a file. It's effectively a git diff, if you're familiar with that terminology, but you store a patch, you build a patch, and then basically you tell Conda, while you're building this code, apply these changes to the code as well, so it can actually go through and complete building. So first thing we did was we modified the source code where we needed to be able to actually get it to compile against the Conda Forge compilers. We then also added a Conda recipe, which is like this build configuration. It explains what dependencies you have to download and how to build FindOrb as a Conda Forge package. And then finally, once you have those two things, you submit a pull request to the Conda Forge feedstock. Somebody looks at it, they say, hey, this looks great. We're going to incorporate those changes, and now the rest of the world has access to this latest version of FindOrb. And what was really nice about this is we managed to get this done from start to finish. However, it took a lot longer than we anticipated. So the first one of the issues we encountered was that the compiler flags that were used by FindOrb by default, so the way that you and I would normally install it, were actually incompatible with the compiler versions used by Conda Forge. This is extremely difficult to solve, and so this took a lot of iteration to actually get working. The second thing is Bill Gray is not somebody that has traditionally versioned his codes. So that means that you can't say, I want to download the version 1 of this repository, which would be a lot easier. So instead, what we have to do was we have to go through the underlying different code repositories that build FindOrb and tag them to a certain commit history. And that's not necessarily hard work, but it is tedious because you have to make sure that the different versions all match and so that the end result is actually something that works. So that requires quite a bit of testing. And here we also kind of started bumping into some fundamental issues with Conda build practices. So a single Conda build, so a single attempt at me or Aditi trying to build FindOrb takes 10 to 15 minutes. That's 10 to 15 minutes for you to sit there and wait to figure out if your build has succeeded or failed or not. And so when you're working on things like versioning and when you're working on things like source code changes, excuse me, it can take literal hours to iterate past that failure, right? You make a change, 10 to 15 minutes later, you see what the result of that change is. You then have to make another change. You have to wait another 10 to 15 minutes. And it means that you have hours worth of work turning into days worth of work, turning into weeks worth of work. It is painful. It's painstakingly slow work. And then lastly, and I'm just going to put this out there, but I don't spend too much time on it. Basically, anything to do with versioning and dependency tree issues in Conda means you are always building from scratch. So you're always paying that 10 to 15 minute price, regardless of what you're doing. But we managed to get through this. This took a lot longer than we anticipated, but we were able to get this project done from start to finish. And this is a huge shout out to Aditi for managing to get this all done. Okay, and that leaves OpenOrb. Again, our starting position here was provided to us by Professor Mario Jurich. And this really goes to show that there are a few people who work on these problems, and Mario is one of them. The issue here is that, again, things were out of date, and we had wanted to get some more features incorporated. When you incorporate more features, that means you're adding new dependencies to the actual build recipe, which overcomplicates things again. And as before, our deliverables were another Git patch, this time written in Fortran, to actually get the code to compile against Conda Forge's compilers. We were also able to build a Conda recipe to effectively build OpenOrb as a Conda Forge package. And from then on, it was just problem after problem. So the first thing was there were upstream changes, things that were way outside of our control, to the Fortran compiler that Conda Forge uses that actually made it so the starting place recipe we had was completely broken. The actual code patch that we started with was also completely broken. So we started from scratch. It turns out that Conda Forge also had a corrupted dependency tree. And so what this ends up meaning is when I ask Conda Forge, hey, can I use your Fortran compiler? Conda Forge will be like, yes, you may use this version. And I'm going to download all these different versions of the dependencies for that compiler. And then we're going to use those to build a package. It turns out that list of dependencies for the Fortran compiler was corrupted. And that meant that it would download dependencies that made the compiler crash when it tried to compile this code. This was extremely hard to diagnose. This took weeks, weeks of iteration again. And yeah, so this is, again, one of those issues that you end up facing. And this is not our fault. This is an upstream error with the actual dependency tree that was maintained for this compiler. And we had to wait until this was fixed upstream to be able to keep making progress. What was also bizarre was these builds manifested differently on Linux and Mac OS X. So I was working on Linux, Aditi was working on Mac OS X. The different compilation, so the different compilers used by the different systems would crash at different points. But we ended up getting this all reconciled. Like we were able to build local Conda Forge packages for OpenOrb, which was a huge success. And then when we finally went to go submit those to test them to make sure they could work on the cloud, they would always crash. And we were never able to replicate the failures on the cloud on our systems locally. And so at that point, that was kind of the final nail in the coffin that ended this project and left it really as status incomplete. We were not able to get past that final roadblock because we were not able to reproduce the errors at all. So that was all kind of doom and gloom. But we did achieve success in 2 other projects. And so I'm just quickly summarize what I just said. So basically, at this point, it's worth noting that Aditi had already worked 3 months past her funding. So huge kudos to her for doing that. For SBPi, we were successful, but we got scooped. That's okay, because the community still benefits from this. For FindOrb, we were successful start to finish, but it took a lot longer than we expected. And then finally, for OpenOrb, we almost got there, but there was just this final thing that we could not solve. And this brings me to an important point here, and that is, this is not pretty work, right? This does not generate beautiful plots, does not generate beautiful papers. All of these slides were text heavy, right? And that's a testament to the fact that this is not pretty work. But the important thing is it's extremely important and absolutely necessary work. We need this to be done, right? We need these codes to be installable. We need easy access to these codes so we can test that they're actually working as intended, so that we can have confidence in our results and confidence in the, confidence that the science that we're pulling out from these packages is actually founded on merit and accuracy. And so that really what this is, it's a call to action for more funding situations like this, where people are not going to package these codes on their own goodwill, right? This only gets done with funding. And an example of a good funding, a success story for this funding is this Kickstarter project. Like, we actually were able to get this done for some of these packages. And that's really a testament to the need for more funding for problems like this. To not end on a complete like kind of doom and gloom note, I do want to point out to some workaround that we came up with, and this is a credit to Aidan. But basically, we don't, in the absence of actually being able to install OpenOrb, FindOrb, and OrbFit completely through Conda, we actually ship Orbit with Binder. Binder is an interactive way of building a virtual machine and then running a notebook on that virtual machine. And the way that this works with Orbit is this. So Aidan created a Binder recipe that installs OpenOrb, FindOrb, and OrbFit all in the same environment. And the way to access that is you click on this little interactive demo button on the Git repository. This will spin up a web page that looks like this. It can take a couple minutes to actually get the virtual machine running. And sometimes it'll crash, so you might have to come back to it. But the more people use this, the faster it builds, because Binder is smart and actually caches these kinds of builds. So please do use it. But once you have this virtual machine up and running, you then get access to this. And this is effectively a notebook that's running Orbit, and you have access to all 3 propagators in the same environment. And as a testament to how well this works, the test results that I showed you at the top of when I started talking were all generated and run inside this Binder environment. So you can reproduce the stuff I did in the first couple slides interactively in in this kind of Binder testing environment. And so on that note, I'm going to pass it over back to Sarah to finish off.
Thank you, Joachim, for explaining all of the very often difficult work that went into these projects. So we just want to wrap up by saying a big thank you to Las Cumbres Observatory and the Heising-Simons Foundation for providing us with the funding and support to be able to do these 2 projects. As Joachim mentioned, this work is really needed for the community, and it's really, really helpful to get funding in order to actually be able to accomplish the work that we were able to do. So we're really appreciative of that. We want to give an extra thank you to the program's Resource Allocation Committee. They provided us with extra funding for our Orbit project that gave us 2 additional months of time and resources to work on this project, that gave us the time and resources to be able to get all 3 of these very commonly used Orbit fitting codes in our list of codes that are supported by Orbit. So we're really appreciative of that extra funding that got us to our completed level, or our goal level of completion with this project. We also received additional support for the Orbit project from the B612 Asteroid Institute, which we certainly appreciate as well, to get us to that level of completion at the end. And of course, we have to give a huge thank you to Aidan and Aditi, who did a huge amount of work with all of this. I also personally want to thank Joachim for being a co-I on these projects with me and bringing all of his level of expertise and hard work with getting these projects as far as we were able to go as well. So thank you from me to you, Joachim, as well. And as Joachim described in quite a bit of detail, there's still a fair amount of work that's left to be done to get these codes to the place where they are much simpler for people to install and be able to use. We're very grateful to Aditi for adding or for working for extra time beyond the funding that she had available to be able to get us to the point we got to. But even so, we are hopeful that there will be opportunities to seek support in the future to be able to hopefully get this work to the level of completion that we were hoping to get to originally. So with that, go to our last slide, just put up a summary here. Again, on the right, here are links to be able to access Aidan's research note on Orbit, how to get to the code on GitHub. And Aidan was also recently interviewed for the AAS Journal Author Series on his research note on Orbit. So if you want to hear Aidan actually talk about Orbit and its capabilities, we encourage you to go to that YouTube link that's in the bottom right-hand corner of the slide here and listen to that interview. Okay, thank you.
Wow, just wow. The body of work that you have put together in this double package of work is just spectacular. I have wrestled with dependency trees myself, and I can completely empathize with the pain you must have gone through in getting this working. So congratulations on everything you were able to achieve. It really is a superbly impressive project. So if anybody has any questions for our speakers, please do post them in the chat and we will bring them up. I do have one of my own, which sort of occurred to me as you were going through, just to get the ball rolling, is you mentioned the Bill Gray in particular. The authors is one of those people that commits continuously. And the same is really true with any package that's in use. It's constantly having bug fixes and upgrades, which means that if you're running a package of unit tests, you really have to use continuous integration tools to constantly rerun those tests and make sure that nobody's broken anything in the meantime. So is that something, I mean, I know you can have workflows managed via GitHub and things like this. Is that something that you plan to do to keep this work in date?
Yeah, I can definitely answer that. So the B612 Astro Institute is really interested in this because they're building a lot of services using these packages. And we actually have somebody working now on converting Aidan's Orb It code into a continuously integrated and tested kind of environment. So this will be running on GitHub. It's going to scan for changes to any of the underlying codes, rerun the set of kind of fiducial tests that we came up with. And the goal is to publish those to a website where you can actually see the table, the version of the code that was used to run and generate those results. And you can actually see how these things are performing in real time. So that is the goal. And there's somebody working on that at the moment. So stay tuned.
Glad to hear that. I'm glad to hear that. It ensures the longevity of the work.
Mm-hmm.
I am curious how on earth you managed to really diagnose that Conda Forge itself had a problem with its Fortran compiler configuration. It would never have occurred to me to try and debug their code.
Yeah, so we had to rely on expertise here, and that expertise was Professor Mario Juric, who had experienced this before for different work.
Oh, really?
And so he pointed us and said, he pointed to us and said, hey, sometimes there are things in Conda Forge that are actually broken. So don't assume that what they're telling you in the errors are actually true. And at that point, we went through and we started manually pinning every single package that was being downloaded as a dependency to a version that we believe to be stable. And that's how we figured out that the dependency tree was broken. What I did not mention was, even though we defined the correct version in the end, Conda Forge would ignore the version that we requested and still download the incorrect one. And that required an upstream fix to actually get working.
Okay, and presumably you had to work with Conda Forge themselves to get that implemented.
So thankfully somebody else had reported this error, and so we were just following along the GitHub issue. But yeah, so yeah, we didn't have to we didn't interact with anyone at Conda Forge directly for this particular error.
Okay, I'm glad it's been resolved. What a tremendous piece of work it really was. Do you have you mentioned right at the end you had you were struggling with some implementations of the cloud. Do you have any hopes for getting that resolved in future?
Yeah. So one of the things that we wanted to get to doing is that Conda Forge actually provides you the Docker images that they're using for their virtual machines.
Okay.
And so we went to that repository to try to download those images and actually see if we can one-to-one replicate the build environment and then see if we can replicate the error. Unfortunately, when we did that, this was at the very tail end, and the images, there was some they were not able to be downloaded for some kind of maintenance reason. At that point, we kind of just put it to bed and said that we couldn't do this. But that's how if I was to go back and solve this with Aditi, that's how I would solve this problem, is to go now to the actual Docker images and see if we can replicate the error. Right there. Yeah.
Okay, so well, hopefully you get support to continue this work in the future, because I can only imagine that the number of people worldwide who would otherwise be struggling to do all of the build and the installation and everything that you have now resolved. Just imagine the amount of man hours and research time that would have been lost and has now been regained thanks to the work that you have put in. So I hope it was all worth all of the pain you went through. And thank you very much, both for your research and for your talk here today. So congratulations again. And that's about all we have time for today. So I hope you will join us again for our next Kickstarter colloquia, which will happen, I believe, Monday next week. And just to finish off, thank you very much, Sarah and Joachim, for your presentation. This has been a terrific talk. Thank you.
Thank you.
Thank you very much.
Bye-bye, everybody.